enough? Right there in the glare. All right, so a function is essentially just a mapping between two sets, right? Take the inputs, do something to them, and you get an output. So a function is some sort of rule that maps a set of inputs to a set of outputs. So our rules will involve the rules of algebra, things like dividing, multiplying, taking square roots. And in some of those operations, we're limited to what types of inputs we can use. The set of inputs are called the domain of the function. And the set of outputs will be the range. We're used to seeing functions pairing x's with y's. So the x's are the domains and the y's are the range. And then a lot of times, instead of using a y, we'll use the f of x notation. You familiar with that? So we take the domain elements, the x's, do something to them, and get y's. And it's even possible to share a y. But our rule is some sort of function that tells us what to do. So when the laws of algebra are violated, the things that we can't do, dividing by zero, taking square roots of negative numbers or even roots of negative numbers, then we have to restrict the domain or describe the domain as a set without those numbers in it. So in the examples that I gave here in problem number 7, we've got 3 functions. The first one does have dividing. F takes x and sends it to 2x over x minus 5. G is a function of t, takes the input t, squares it, subtracts it from 4, and then takes the square root of it. And h is a trig function. Takes the tangent of some number x. And the instructions are to give the domain of each of those. So on the first one and the third one, we have to just make sure that we don't divide by 0. And you look at the tangent and think, well, we're not dividing there, but we are, right? The tangent is described as the sine of x over the cosine of x. So we cannot divide by 0, but everything else is fair game. Doesn't matter if I have a 0 on the top, I just can't have a 0 on the bottom. Can you eyeball this and tell me what value of x makes the bottom 0? So x can be any number other than 5. So we can say the domain is the set of all x other than 5. Now, if you're doing this on web work and it wants things written as an interval, then we'll just write the entire number line from -infinity to +infinity, but we omit the 5 with the parentheses like that. It's the whole number line, but with the 5 taken out. So this third one is also a function that has division. And so our idea is, again, we can't divide by 0. So here's what we're thinking about now. For what values of this variable x will the cosine be 0? Yes, sir.
We've got nothing.
I figured.
Yeah,
Thank you very much. So we'll try to squish the desks together
I'll,
after we're done.
yeah, we'll figure it all out.
Okay, at least I have a board. Last semester, they put me in the foreign language building and I walked into the room and it had like a stage. That's going to be good. No board. So just oral math. I have that moved right away. Okay, so let's think about trig again. I'll go more into trig, but the cosine, if we talk about unit circle trig, on the unit circle, the cosine corresponds to the value of x at which the angles intersect the unit circle, different x than this x, but where is the, I don't know how to tell you how to say this. Where in the coordinate plane are all the x's equal to 0?
Pi over 2 and 3 pi over
That's right, anywhere on the y-axis. So angles that intersect the y-axis would be the 90-degree and the 270, which are pi over 2, 3 pi over 2, any of those odd multiples of pi over 2, right? Because these are circular functions and there are an infinite number of them. So we're going to say x cannot be, so cosine of x is 0 when x is any odd multiple, odd multiple of pi over 2. So that's the numbers that we have to throw out. So we're going to say x cannot equal to, now let's get odd multiples of pi over 2. So I'm going to let n represent a counting number, any counting numbers, or even non-counting numbers, integers. 0, 1, 2, 3, -1, -2, -3, and so on. Take any integer and double it, and you got something that's even. All the odd numbers live right next to the even numbers. So all I gotta do is back up a bit, and now that is always going to be an odd number. Right? Try it. You people in computer science know that we use the n as a dummy variable, and then that generates a sequence of numbers. Can you believe that they're all going to be odd? And then multiply, so we multiply by pi over 2, and so I have to throw all of those out. Good. Now for the middle one, there's no division, but we do have the operation of taking the square root. Any even root can only be done on positive numbers. So in this one, we need the stuff under the radical sign to be positive. We can take the square root of 0, so I'll go ahead and include 0 in that. But now think about how we did these nonlinear inequalities last time. You can either think of this as being geometric. Think of that 4 minus t squared as an upside down parabola, and then figure which part of that parabola lies above the axis. Or you can factor it and use the cut point method and make a number line and decide where those expression is going to be positive. So I'll do the factoring part. If I factor that, I can factor that as 2 minus t times 2 plus t. And I know that that's 0 when t is -2 and when t is +2. And now we're going to plug some test points into these two factors, multiply them together, and decide whether we get something positive or negative. So if I put, say, a -3 here, 2 minus a -3 is positive. 2 plus -3 is negative. So when you multiply a positive with a negative, you'll get something negative. If I put a 0 in for t, each of those factors is positive. 2 positives multiply to a positive. And if I put, say, a 3 in for t, my first factor is negative, the second one's positive, so the product is negative. So you can see the product is going to be positive for these values right in here. And we'll keep the endpoints. And so that's our domain. Anytime you use a number between -2 and 2. You familiar with all of that? Okay, while we have some functions up here, what if I ask you, using these three functions, to find f of 4 minus g of 0? You know what I'm referring to there. Tell me what f of 4 is going to be.
2 times 4 over 4 minus
2 times 4 over 4 minus 5. You go to the rule for F, use that as the input variable. Now we follow the pattern, go over to G, put 0 in where the variable is. So we'll just get the square root of 4 minus 0 squared. So here I get 8 over -1. Square root of 4 is 2. So that expression is equal to -10. Now I don't have to do this with numbers. I can do this with symbols. What if I asked for, say, F evaluated at z squared? Rewrite F, so now it's a function of z squared. Call out what that would look like. Or not, just sit there.
Would it be 2z squared over z squared minus 5?
Right, use that as the input variable. 2z squared over z squared minus 5. Okay, so I can put whatever I want in there. Could be an algebraic expression, could be another function. What if I wanted to find h of g of t? Well, sometimes that's written with a little tiny circle, h of g. Let me make my circle smaller so it doesn't look like I'm spelling hog, of t. You know what that means? It means use this as the main rule, which takes the tangent of the input. But as your input, use this. So I'm going to put the square root of 4 minus t squared here. That's not multiplication, that's the tangent of the square root of 4 minus t squared. You remember how to read function notation, do composite functions, combinations of functions? We're all good? So you want to spend a little bit of time talking trig? Let's review some trig. All right, I'm going to erase all this. And we're gonna subdivide the unit circle. Remember that radian measure is based upon the fact that we're dealing with a circle of radius 1, whose circumference is 2 pi times 1, 2 pi hours of circumference of a circle. So I'm giving you a circle whose radius is 1. So the total length around this circle is 2 pi. If you take an angle and put its ray with the endpoint at the origin and rotate that around the circle 1 complete lap, we formed an angle of measure 2 pi. When we talk about degrees, how many degrees are in one complete circle? 360. So if I did that entire lap around the circle with that ray, then I form an angle of measure 360 degrees. Try to erase this here. So, what we're talking about since it is the unit circle, it has as its equation x squared plus y squared is equal to 1. And it intercepts the axes here at 1, 0, here at 0, 1, here at -1, 0, and down here at 0, -1. So I want you to imagine a ray with an endpoint hooked at the origin And this particular ray that is my expo marker would have measure of 0 degrees and 0 radians. If I rotate that all the way around the circle, coterminal with that positive x-axis, I formed an angle of measure 2 pi radians or 360 degrees. So if I just rotate it to the negative x-axis, then I form an angle of measure pi radians. So on this little chart here, I've given you the ordered pairs. So fill in the ordered pairs at the coordinate axes. And then it says inside, there are 2 blanks here, one for radians and one for degrees. So if I rotate from here to here, I've gone pi radians. I'm going to put them out here instead of inside the circle, because pi was half the entire circle. So how many degrees is pi radians? 108. So that's 180 degrees. If I rotate my angle counterclockwise, the angle has positive measure. If the angle is rotated clockwise, the angle has negative measure. We can denote these angles in an infinite number of ways. So another way to denote that angle rotating this way would be negative pi radians, or negative 180 degrees. Okay, so take your ray, rotate it a quarter of the circle. How many radians is this? Pi over 2 or 90 degrees. Degrees, not squared. Now rotate that ray 3/4 of the way around the circle. So what angle measure is formed with the positive, the negative y-axis? Say it again. 3 pi over 2 or 270 degrees, 3/4 of 360. And if I get all the way back here, then I'm either at 0 radians, which is 0 degrees, or 2 pi radians, which is 360 degrees. Okay, now what I want you to look at is drawing the line y is equal to x and the line y is equal to negative x. That's the line through the origin that intersects at a 45-degree angle, right? That's a 90-degree angle, goes smack dab in the middle at a 45-degree angle. Same deal here. There's the line y is equal to negative x. So if this is a 45-degree angle, we need to figure out how many radians that is. So how do you convert from degrees to radians? We use the conversion that there are pi radians in 180 degrees. So if I want degrees to cancel, I'd put the 180 degrees down here and the pi radians up there, so that my degrees cancel. And I have 45 pi over 180 radians. But that's going to simplify. 2 times 45 is 90. So 4 times 45 is 180. So 45 cancels into 180 and gives me pi over 4. Which makes sense. I cut the top half pi radians into quarters. So this is pi over 4 radians. So think about it, 1 pi over 4, 2 pi over 4 gives us pi halves. This then is 3 pi over 4. And pi would be 4 pi over 4, making this one 5 pi over 4. 6 pi over 4 is here, 7 pi over 4 is here, and then that one's 8 pi over 4. Now we can do the same thing with the degrees, keep adding 45. 45 plus 45 is 90. 90 plus 45 is 135. 135 plus another 45 is 180. Here's where the arithmetic gets hard. 180 plus 45 is 225. 225 plus 45 is 270. 270 plus 45 is 315 degrees. Okay, on this line here, that's the line where y is x. X and y are the same there, 45-degree angle. So if y is the same as x, I can find the ordered pair here by putting an x where the y is. So I have x squared plus x squared is 1. So this is along y is equal to x. And so I have 2x squared is 1, or x squared is a half, which says x is plus or minus the square root of a half. Square root of 1 is 1. So I can write that as plus or minus 1 over the square root of 2. And if we rationalize the denominator, then I get x is square root of 2 over square root of 4, which is 2. I kept the positive because I'm in the first quadrant. So I know x right here is the square root of 2 over 2. But x on that line is the same as y on that line. So that ordered pair there is also square root of 2 over 2. That gives us all of the coordinates. All we have to do is adjust whether x or y is positive or negative in those quadrants. In quadrant 2, x is negative, y is positive. So the ordered pair here has a negative square root of 2 over 2, positive square root of 2 over 2. Back here, x is negative, y is negative. So at 225 degrees, both components of the ordered pair are negative. And over here, both are positive. I'm sorry, x is positive, y is negative. Agree? So what we've just seen are the ordered pairs at the coordinate axes and then at the mid angles of those coordinate axes. And in our definition, the first member of the ordered pair is the cosine of whatever angle we're talking about. So I'll use a theta to denote the angle. So in our ordered pairs, the cosine is the first member of the ordered pair. The sine is the second member of the ordered pair. So if I want the sine of 7 pi over 4, I'm here on my unit circle at the second member of the ordered pair. Sine of 7 pi over 4 is negative square root of 2 over 2. Good? Okay, so now what we're going to do, try to ignore those blue lines. Ignore the blue lines and take this arc here, which is 90 degrees, and cut it up into 3 equal pieces. So each piece would have length of 30 degrees. Right? So if I ignore that blue line, let me get some red lines going here. If I try to subdivide that up, then I'd have one about right there and maybe right there. So if I draw this line back, that angle would be 30 degrees. And draw this line. That angle would be 60 degrees. So 30, 60, 90. Now keep this highly accurate measuring device going, and let me keep going around the circle here. So from 90 to here. 90 plus 30, 120, 120 plus 30. So now I've made the 120 degree angle and the 150 degree angle, and I'm going to try to draw a straight line here and here. So 60, 90, 120 and 150. And then notice that 150 plus 30 brings us down here to 180. 180 plus 30 puts us here. 210 plus another 30 puts us 240. 240 plus 30 puts us, see my measurement got kind of skewy. That should be the same width as that. Gives me 270. 270 plus 30 makes this one 300. 300 plus 30 makes this 330 degrees. In radians, I cut these up into thirds. So 1/3 of pi halves is pi sixth. So 30 degrees is the same as pi over 6. So this is 1 pi sixth. The next one will be 2 pi sixths. 2 pi sixths is the same as pi thirds. Then 3 pi sixths. Agree that it reduces to pi halves. 4 pi sixths, reduce that for me. And you'll get 2 pi thirds. The next one's 5 pi sixths. And pi is 6 pi sixths. Keep counting. 210 degrees now puts us at 7 pi over 6. And then 240 would be 8 pi over 6. 8 and 6 are both divisible by 2. So we're at 4 pi thirds. 8 pi 6, this puts it 9 pi 6. Reduce that to 3 pi halves. 300 degrees is 10 pi 6 or 5 pi thirds. And now we're at 11 pi 6 here. And 12 pi 6 is 2 pi. And now we need the ordered pairs there. So let's see, how am I going to do this for you? Let's look at an equilateral triangle. What is an equilateral triangle?
All sides are the same.
All sides are the same. And
All in.
all angles are the same. How many degrees are there in any triangle? 180. So if they're all going to be the same, don't they all have to be 60 degrees? Right. Now let's suppose that each of these lengths is 1 unit, so that I can make it fit my unit circle. If I drop the perpendicular segment down from here in an equilateral triangle, the altitude bisects the vertex angle and it bisects the opposite side. So now I have a 30-degree angle here, a 90-degree angle there. And this length is now 1/2, and we can figure out that length. So let's figure that length out. H squared plus 1/2 squared is 1 squared. Pythagorean theorem. We'll solve for H. So H squared is 1 minus 1/4. So H is the square root of 3 over the square root of 4, which is the square root of 3 over 2. Now remember, in our right triangle trigonometry, if you have a right triangle, which we do looking here at the left portion, remember that the sine of any angle is equal to the side opposite that angle divided by the hypotenuse. And the cosine of any angle is the adjacent side divided by the hypotenuse. So using that picture, and the fact that my ordered pairs are this way, let's figure out the cosine of pi over 6 or the cosine of 30 degrees. The cosine of 30 degrees is the adjacent side over the hypotenuse. So what do you have for me? Square root of 3 over 2, because the hypotenuse has length 1. So the x coordinate here is the square root of 3 over 2. The sine of 30 degrees is the opposite side over the hypotenuse. So the ordered pair there is 1/2, or the second member of the ordered pair. Now for every something over 6, the ordered pair is the square root of 3 over 2 1/2. All we gotta do is adjust the plus or minus sign on the x and y coordinate. So if I go over here to 5 pi over 6, I went back in the x direction, up in the y direction. So I have the ordered pair negative square root of 3 over 2, positive 1/2. I don't know where to put it. The next pi over 6 is down here. In the third quadrant, both x and y are negative. So we're going to write negative square root of 3 over 2, negative 1/2. And then the next pi over 6 is over here where x is positive, y is negative. So we have square root of 3 over 2, 1/2. All good? To get the ordered pair here, let's use our equilateral triangle over there and look at the cosine of 60 degrees as the adjacent over the hypotenuse. So here's my 60 degrees. The adjacent side has length 1/2. The hypotenuse has length of 1. So the first member of the ordered pair there is 1/2. Bet you $1, the second member of the ordered pair is square root of 3 over 2. Because remember, they still have to satisfy that relationship that the x squared plus the y squared is 1. So all of the pi thirds have that ordered pair with the x negative in quadrant 2, x and y negative in quadrant 3, y negative in quadrant 4. So you can finish your unit circle that way. This is negative square root of 3 over 2, positive 1/2. My 240 is in quadrant 3, so that's negative square root of 3 over 2, negative. I just wrote the wrong one. I want 1/2. Take that back. What I say, negative 1/2 square root of 3 over 2. Down here, I have both of them negative. Negative 1/2, negative square root of 3 over 2. And this 300 degrees here. X is positive 1/2, y is a negative square root of 3 over 2. But if you know these, you know all of them just because where they are in the unit circle. Okay? So on the back side here, yeah, you can almost see that picture, huh? Let's see if you can use your unit circle now and figure out on number 8 the following values without using your calculator. So use your circle or your knowledge of right triangle trigonometry, however you can do it. See if you can get me numbers for parts A through H, and I'm going to write them up here for the purpose of the Zoom. Today, you can do this with the unit circle. From here on out, you'll do it just in your head. And I said last time that if you know those angles in the first quadrant with the ordered pairs, you know them all. Remember, I put them in a table form. I'll do that table one more time. Add my angles. And then even though the sign represents the second member of the ordered pair, I always put the sine first and then the cosine second. So that, remember, I can do that counting thing. But I start at 0. I'm going to put these in radians. Pi over 6, pi over 4, pi over 3, pi over 2. Then I counted 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Took the square root of everything, divided by 2 and simplified. And I got 0, 1/2, square root of 2 over 2, square root of 3 over 2, 1. And then these go backwards. 0, 1/2, square root of 2 over 2, square root of 3 over 2, and 1. So all you really need to know is that if you have one of these as your reference angles, the angles in here have measure pi minus the reference angle. The angles in here, if these angles are theta, the angles down here are pi plus the reference angle. And then down here, they're 2 pi minus the reference angle. And all of the trig functions are positive here. The y coordinate is positive here. Cosine corresponds, sine corresponds to the y coordinate, so sine is positive here. Its reciprocal will also be positive. What's the reciprocal of sine going to be? Cosecant. X and y are negative here, so the only one that's going to be positive here is the tangent and its reciprocal. Cotangent is the reciprocal of tangent. In the fourth quadrant, x is positive, y is negative, so cosine is positive there, and 1 over cosine is the secant, it'll be positive. So if you know these and the fact that all students take calculus, then you can remember where you have positive and negatives. All are positive, sine is positive, tangent's positive, cosine's positive. Okay. All right, so with that in mind, I know that 7 pi over 4 is pi over 4 short of being 2 pi. Pi over 4 short of being 2 pi, since 2 pi is 8/4. So I know that's a quadrant 4 angle. And in quadrant 4, the sine's going to be negative. I know pi over 4 was the y is equal to x. The only place that y and x are the same are here, the square root of 2 over 2. So that makes it easy. The negative square root of 2 over 2. Pi is a quadrantial angle. So pi takes me back to the negative x-axis. On the negative x-axis, the x coordinate, or the first member of the ordered pair, is a -1. Pi over 4, that's the line y is equal to x. Tangent is the ratio of the y to the x. So square root of 2 over 2 divided by square root of 2 over 2 is going to be 1. Tangent is the sine over the cosine. Sine and cosine are the same right there. Tangent of pi. Tangent of pi is going to be the sine of pi divided by the cosine of pi. So pi again was a quadrantial angle. That's the negative x-axis. The sine was the y coordinate. The y coordinate there is 0. The x coordinate was -1. 0 divided by -1 is 0. So far, so good? Secant is 1 over the cosine. So the cosine of pi over 3 is 1/2. This is going to be 1 over 1/2. And that's going to be 2. Okay. Cosine of 5 pi over 6. Can you tell me which quadrant 5 pi over 6 will be in? Quadrant 2 based upon your circle, or it's not quite 6/6. right? It's 1/6 short of being pi. So that puts us in quadrant 2. Only the sign is positive there. So I know for a fact that this is going to be negative because it's in quadrant 2. Now I can look at my pi over 6 and see the cosine is square root of 3 over 2. Not from here. The cotangent of pi over 6 will be the cosine over the sine of that angle. On my table, the cosine squared of 3 over 2. The sine is 1/2. So when I'm dividing by a fraction, remember that we can flip the denominator and multiply. So the 2's will cancel. And that just leaves us with the square root of 3. Cosecant of pi over 6 is 1 over the sine of pi over 6. And then the sine of pi over 6 is 1/2. 1 over 1/2 is going to give me 2. Okay. It's all good? All right, another quickies that you always need to know. I'll put my camera this way so I can do some more board. Is where our trig functions are 0. So for what values of x is the sine of x equal to 0? On the unit circle, the sine is the y coordinate. So where is the y coordinate always going to be 0? 0, pi, 2 pi, 3 pi, every multiple of pi, right? 0 plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. Any multiple of pi. Where's the cosine going to be 0? At the pi over 2's. All of them, right? The odd multiples of pi over 2. Remember, we wrote the odd multiples of pi over 2 as 2n minus 1 times pi over 2. What makes the tangent equal to 0?
Cosine review.
Other way,
Oh, sorry.
right? Because tangent is sine over cosine. So it's wherever the sine is 0. So it's all the same places here. The reciprocal of the sine and the reciprocal of the cosine are the cosecant and the secant. Those values are never 0. Right? There's no way I can flip over the sine and make it equal to 0. A fraction is 0 only where its numerator is 0. So the cosecant is never 0. Same with the secant. It's never 0. But the cotangent is 0 where every place the cosine is 0. Right? Cotangent of x is 0. Every place the cosine is 0. If I asked you to quickly sketch the graph of the sine of x, the cosine of x, and the tangent of x, could you do it? Yes, no, maybe? Let's do it real quick. Move that table back again. Let's do the sine of x first, using this. All right, one period is typically of length 2 pi. So that's 2 pi. That's pi. That's 0. Do it again. That's negative 2 pi, negative pi, 0. As its max and mins at pi halves. And that's at 1 and at -1. So that's the graph of y is equal to the sine of x. Agree? There's no way, it keeps doing that same thing over and over and over and over. The cosine is that graph shifted left pi over 2. There's 2 pi. In the middle here where it hits -1 is at pi, and then 0, 1. Pi, -1, crosses at the pi halves. Draw that again over here. There's a cosine. Tangent. Is 0 all the same places that the sine is? What happens at the pi halves? What's the tangent of pi halves? What's the tangent of 3 pi halves? Well, a minute ago, when we talked about the domain of the tangent, we said tangent can never equal any of the pi halves, right? Because that makes the denominator 0. What does that look like geometrically on the graph? It's an asymptote. It's a vertical asymptote. So the tangent function is going to have these vertical asymptotes at all the odd multiples of pi halves.
I missed yeah, why'd you have to take this one? Yeah.
So here's one period of the tangent function. And then the rest of them look just like that. Okay. Okay, so why did I draw those? Because now I want to talk about inverse functions. An inverse function is a rule that takes the y's back to the x's. Function takes x's to y's, its inverse takes the y's back to the x's, with the disclaimer that each y can only have one x. Those functions where each y can have only one x are called one-to-one functions. So for instance, if I have this function, just some plain old linear function. If you were to draw that graph, y is equal to mx plus b, I have a straight line, slope of 5, y-intercept of 7. So it's a pretty steep line. But if I run a horizontal line through y values, those horizontal lines is going to hit this diagonal line once. That makes it one-to-one. Something that's not one-to-one would look like y is equal to x squared is not one-to-one. Because if I say, if y is 4, tell me some x's that make that equation true, you're going to come up with more than one of them. If y is 4, what's x? 2 or -2, right? That's a problem. So when I run a horizontal line, I found 2 x's that go with that same y. If we have functions that are one-to-one, I can reverse the pairing that gives you the x for a particular y. For instance, if this is my y value here, and if I said what x corresponds to y is 17, you could find it just by putting 17 here and solving for x. So if I have a 17 here, I subtract 7, I get 10, divide by 5, I get 2. So this line has one of its ordered pairs to 17. The inverse does it the other way. The inverse is a function, a rule that takes the x's and makes them the y's, takes the y's and makes them the x's. So for this particular function, the inverse takes the ordered pair and makes it 7, 0, and then takes the ordered pair 17, 2. So here's the graph of the inverse function. Whoops, I missed that one. We just employed the big dot principle. So if this is f, this is its inverse, which we denote with the superscript -1. We find it by doing what I just said. The rule for f inverse made these guys the x's and these the y's. So I'm going to find that rule by doing that. I need those pictures there. So I'm going to find f inverse. So first, make y into x, x into y, and then solve for y. So I'm going to put an x over here, a y right there, and I'm going to solve for y. Subtract 7. Am I off the picture? I am off the picture. So watch this. Subtract 7. X minus 7 is equal to 5. Y. X minus 7. And then I'm going to divide by 5. And that's my rule for f inverse. And you can make a quick check. When x is 7, right here, f inverse is 0. When x is 17 right here, 17 minus 7 is 10 divided by 5 gives me 2. 2 points uniquely determine a line, so I've got it. And these two functions have the property that they undo each other. They peel the other's rule off. So what I just said was that any two inverses satisfy the fact that if I take the composite function, this peels that rule off and gives me back what I started with. Same thing the other way. Peels it off, gives me back what I started with. That would happen here. If I want to find, for instance, using this example, far back can I go? I'll do it here. If I want to find f inverse of f of x using our example, I apply this rule, which takes input minus 7 divided by 5. As the input, I use the 5x plus 7. These two 7s subtract each other out, 5x over 5, bam, there's the x. They undo each other's rule. Remember all that? If I want to find the inverse of this function, I have to make it 1-to-1. So in other words, if I want to find the inverse here, I can find an inverse for x greater than 0. I can find an inverse for x less than 0. If x is greater than or equal to 0, my inverse function takes all of these ordered pairs and flips them. And I should get something that looks like this. So that's f, that's its inverse. You remember that the graph of f inverse is the reflection of the graph of f along the line y is x. Is that something you've heard before? If I painted that line and folded this board on the diagonal, the blue would be the imprint that that wet paint would leave when I unfold it. Right? So if I consider x to be positive and I want to find the inverse, I make that the x and that the y. Then I take the square root of both sides. Now, when you take square roots, you get 2 square roots. But if x is positive, so is y. And so I get, that's the inverse over here. What do you think for this piece? If I call this one f Uh-oh, that was not good to leave the top off. What do you think the inverse would look like for this half? What's the equation for here?
X squared.
This is x squared where x is negative.
Is it 1 over x squared?
Wouldn't be that. Here I had the option of which root to take. This would be the other option. Right? Negative square root of x. Now, the reason I pointed out the one-to-one functions is that we have inverse trig functions. But to find inverse trig functions, we have to throw away good portions of these graphs. We have to keep a one-to-one piece of these two functions, even this one, and then we can define an inverse sine, an inverse cosine, and an inverse tangent. So we're looking for a piece of, say, this graph that the sine takes on all of the values between -1 and 1, and we have a one-to-one piece. There are many places. By convention, we take this piece. Have all the values of the sine function right there. And now I can define an inverse sine function. For the cosine, I want to go through all the numbers from -1 to 1, which this was the cosine. Yes, this is the cosine. And so we take this piece. And for the tangent, we just take the first period, that piece. Throw the rest of it away. If we do that, we can define the inverse functions. And so I'm going to do that right now. So to define inverse trig functions, we must restrict the domains as shown in red. For the sine function, we're taking x to be between -π/2 and +π/2. And when we do that, we get the y values between -1 and 1. For the cosine, we keep the x's between 0 and pi. And when we do that, my y values are between -1 and 1. For the tangent, we use a strict inequality between -π/2 and π/2. And notice that the tangent can take on any negative number and any positive number. So the y values here are between plus and minus infinity for the inverse tangent, or for the tangent. The inverse trig functions swap sets. This becomes the domain of the inverse sine function, and it has these as its outputs. This becomes the domain of the inverse cosine function, and it has those as outputs. And the domain of the inverse tangent is all values of x. The range will be angles between -π/2 and π/2. And so we have the inverse sine of any input x, where now these x's are those guys, is an angle y if and only if the sine of that angle is that number x.
Here's what I found.
Tell me what you found. I'm curious. 'Cause I don't even know what I asked. Basic geometry, how to find an angle of a, come back, of a line. My watch is doing math. I got a nerdy watch. Okay, so what did I just say? These numbers X are those. X is a number between -1 and 1. But Y has to be an angle between -pi-halves and pi-halves. So the outputs of the inverse sine function are always acute angles. And so I want you to find for me these values, the inverse sine of 0, the inverse sine of 1, the inverse sine of -1, the inverse sine of a half, and the inverse sine of -1/2. The inverse trig functions take real numbers and spit out angles. So now you're thinking of that little table that I had up here backwards. I erased it. What angle do I take the sine of to get 0? But it has to be an angle that is between, where is this on the unit circle? It's going to give me these angles if this number is positive. It's going to give me these angles if this number is negative. So where in this picture am I getting the sine 0? Sine of what angle in that picture is 0? 0. Sine of 0 is 0. That's 0. So I'm looking for an angle here that I take the sine of to get 1 in this picture. Pi over 2. Inverse sine of 1 is pi over 2. Don't work too hard. Look at my arrows. What do you think the inverse sine of -1 is? Follow the arrow. I can't go here. I have to go here. Negative pi over 2. Always acute. Acute meaning less than 90 degrees. Right? Or 90 degrees if it's a right angle. Right? All right. Where in the first quadrant is the angle that I take the sine of to get a half? Pi over 6. So the inverse sine, 6 I said. The inverse sine of a half is pi over 6. So now don't think too hard. What angle do I take the sine of to get -1/2? Negative pi over 6. I have to just go fast backwards. The inverse tangent is going to work the same way because I have the same range between negative pi-halves and pi-halves. The inverse cosine's a bit trickier. So we define the inverse cosine as being the inverse cosine of a number between -1 and 1 is an angle between 0 and pi. So if the number that I'm taking the inverse cosine of is positive, you're going to give me a first quadrant angle. If the angle that I'm taking the inverse, if the number that I'm taking the inverse cosine of is negative, you've got to give me a second quadrant angle between 0 and pi. So let's erase that. We'll do that right here. How much time I got here? Got 3 minutes. I write down the same thing. I write down that the inverse cosine of any input x is a number y if and only if, here's how we abbreviate if and only if, just get rid of the only, squish the ifs together. If and only if the cosine of that number y is x, where these x's are always between -1 and 1, and these y's lie between 0 and pi. So I'm going to find the inverse cosine of the same set of numbers. The inverse cosine of 0, the inverse cosine of plus and minus 1, and the inverse cosine of plus and minus a half. So think backwards. The number that goes here is something that I take the cosine of to get 0. Cosine of what angle is 0? 90 degrees. We're going in radians, so we got pi over 2. Okay, what angle in here? What angle? That's a y. What angle in here am I taking the cosine of to get 1? 0. All right, what angle in here am I taking the cosine of to get -1? Pi. Good. All right, what about the 1/2? Pi thirds? Excuse me. What about -1/2? 2 pi thirds. It has to be a quadrant 2 angle. Look at the way we've got the inverse cosine between 0 and pi. Now I know there are other angles coterminal with these, but it has to be the one in quadrant 2. Okay? The inverse tangent follows like that. Now, a lot of us think of a -1 power as a reciprocal. When it's used on the trig functions, it's not a reciprocal. It's an inverse notation. So to offset that problem, sometimes instead of writing inverse sine, we write arc sine. Same deal. If you see the word arc, it means inverse of. Arc sine, arc tangent, arc cotangent. Okay? All right, we'll do a little bit more. We still haven't finished the sheet. Do a little bit more, I guess, on Wednesday. Is Monday MLK Day? So there's no class on Monday. I know you want me to come, but I'm not going to. But we'll pick this up on Wednesday and we'll get it finished right quick. But has everybody tried to log into WebWork? Everybody's been successful? Good? All right. Enjoy your long weekend. Thank y'all. No trip. Let me get the point out of the way.